In this lecture, we continue our discussion on inviscid and viscous flows, which we initiated in the previous lecture. So, last time you will recall that we derived an expression for substantial derivative. We did it for a density field, but it applies on any other field that could be of our interest in a fluid field. So, the next step that we will take is we will have a look at our conservation equations that we derived in an earlier lecture, the conservation equations of mass, momentum and energy, and at least for mass and momentum we will derive it in class, and you can do it as a homework for the energy equation later on, that how they can be represented in terms of the substantial derivative. So, let us start that process. So, we will keep the substantial derivative operator in front of us, so that we can remember what it means. So, it takes care of the local time derivative of the dependent variable, plus it is the v dot del which will apply on the variable that is of interest to us. So, remembering that, let us try to see how the substantial derivative can be incorporated into the mass conservation equation, that is continuity equation. Okay. So, we will make use of the form of the continuity equation, which is valid at a point in the flow field. So, we are not using the integral form, but rather the differential form. Now, we will expand this term, the divergence term. So, divergence of rho times v is rho times divergence of v plus v times gradient of rho. This is a vector identity. Having said that, if you substitute it here, what do you have? Del rho del t plus, we will take the second term first and this term then next and put it. Why do we do it that way? Because you can recognize this part as substantial derivative of rho. You can see the operator del del t and the v dot del operator here, like we have mentioned in this equation, which means the continuity equation in the substantial derivative form can be represented like this. Let us do it for the momentum equation next. We will take the x momentum equation and do it. So, for the x momentum equation, how does it work out? First, let us write down the x momentum equation again as it is valid at a point in the flow field, that is the differential form of it. Remember that this is a scalar part small u, the pressure gradient, and if you recall the viscous forces with an underline here, because you remember that was the form which was inside the volume integral. Now, incidentally, for the x component of the momentum equation, it can be shown that this term, that is the f x underscore, can be represented in terms of spatial gradients of the normal and shear stresses that we discussed the other day. We will just change the nomenclature of this term. This one we had called it as sigma xx. So, in some books you will find that all of them are represented in the form of taus, while in some others you will find that the normal stresses are represented by sigmas, while the shear stresses are represented by taus. So, let us be familiar with both kind of nomenclature. Now, let us see how we can incorporate the substantial derivative in this equation. And once we learn to do it for the x momentum equation, we can similarly do it for the other components of the momentum equation. First thing first, we expand this time derivative term. Since it is a product of rho u, you can expand it this way. And then the divergence term. In the divergence term, what we will do is, we will break it in such a manner that one part of it is considered as the scalar part, the other as the vector part. We will consider u as the scalar and the product rho times v as the vector. Taking it that way, we are applying the divergence. So, for clarity we can even write it that way. So, it becomes u times divergence of rho v plus rho v times dot product of gradient of u. That is how it works out. Okay. Now, let us see if we put them together, what we get out of it. So, we will not write the right hand side time and again, we will just mark the right hand side as RHS, which comprises of these terms. We will just work on the left hand side. So, left hand side, what are we left with? Rho del u del t, u del rho del t, that is this part, and then comes the next terms which we have written here, that forms the entire left hand side. So, in this left hand side, if you rearrange the terms, you will find it is rho del u del t plus, we will take the two terms which have u over here and we put them into a bracket. It will help us to recognize what it is. So, this is the left hand side, and you may recall that as per the continuity equation, this is equal to 0. So, by mass conservation, this has to go to 0. So, what are you left with? You are left with this and this on the left hand side. Now, if you take the density as the common term, the left hand side gives you rho times within brackets del u del t plus v dot del u. So, what is that? That is recognizable now. It is rho times del u del t. So, the substantial derivative now figures over here, and that is equal to the right hand side terms that we have written on top. So, this is essentially the x momentum equation in substantial derivative form. Now, what is del u del t? Let us try to address this issue. We are following a fluid element, a very small fluid element through the flow field. So, we are tracking a moving fluid element and we are taking a substantial derivative of it. So, that is giving us the time rate of change of the u component of velocity of that moving fluid element, which must be its x component acceleration. Let us call it a x. Similarly, it will have other components of acceleration in a typical 3-dimensional flow field. For example, capital dV dt will be a y, dw dt will be a z, and so on. So, as far as the x momentum equation is concerned, we can now write it as density times x component of acceleration is minus del p del x of sigma x x del y of tau y x del z of tau z x. And then we of course substitute the complete expressions of these normal and shear stresses, but that is not of immediate importance to us. That is why we are leaving it in this form, which is more compact. Now, what have we got in this equation? We have got something like something similar to force is equal to d dt of m v from Newton's second law. So, we are talking about an acceleration of the fluid element, which is produced by virtue of forces which are acting on it. Now, if you look at the forces on the right hand side, del p del x is the pressure gradient along the x direction. What happens if it is less than 0 or if it is greater than 0? A less than equal to 0 del p del x will create a positive term here on the right hand side. That means a force which will accelerate the fluid element. So, this leads to acceleration of the fluid element. However, if del p del x is greater than 0, you have a negative contribution on the right hand side, and that will certainly lead to deceleration of the fluid element. We have seen the effect of favorable and adverse pressure gradient on the state of a viscous flow earlier. Favorable pressure gradient assists the flow, while adverse pressure gradient resists the flow. We have seen favorable pressure gradients influence on the lower surface of the airfoil where the flow was attached. So, it led to attached flow. We have also seen the effect of adverse pressure gradient on the upper surface of the airfoil, where we have seen separated flow or detached flow. You will come across different terms in the literature, they mean the same thing. Always remember that the viscous terms always resist the flow, because they are playing the role of friction, which opposes the state of motion. So, viscous terms decelerate the fluid element always. Therefore, in viscous flows, it is very important that you have a favorable pressure gradient or a neutral pressure gradient. Any time that you are going into an adverse pressure gradient situation will be detrimental for the flow to remain attached on the surface, and the consequent problems which occur due to flow separation, like loss of lift, increase in drag, and so on. Usually for low speed flows, you have a guideline. If it is a flat surface, that means as you move along the surface, there is no change in geometry. That means the wall does not move into the flow or away from it. the pressure remains constant, while if it slopes up for low speed flows, a sloping up of the surface would lead to dP ds less than 0, that means a favorable pressure gradient. A sloping down on the other hand is going to lead to an adverse pressure gradient, which is bad for the flow. And now you recall that this is what was happening on the lower side and this was happening on the upper side of the airfoil. Please keep it in mind that this works for low speed flows. There are more complications in high speed flows, and let us not draw conclusions on how pressure would change in high speed flows like the way we discussed here. It is going to be different from this because of the presence of different waves in high speed flows, especially shocks and expansions. So, we have understood about the acceleration of the fluid element under the effect of pressure gradient and also the effect of surface geometry. Now, let us try to look at a situation where we can identify Reynolds number in the governing equation and see what happens when Reynolds number becomes very high, whether the flow can be treated as devoid of viscous effects at very high Reynolds numbers or not. So, for that we will take the momentum equation, but in a very simple form, so that it is easier for us to work out the connections without adding complexity. We will take two dimensional steady viscous flow, but we will assume that it is having constant density. You may recall that in another lecture we had discussed the context of constant density. We said that in gaseous flows we do see density changes, but then those density changes could be nominal if the pressure changes are not very significant. So, keeping that in mind, we once again write down that relation which we mentioned in an earlier lecture. So, though the compressibility is high for gases, but if the pressure changes are nominal, then the density changes are negligible, and pressure changes are nominal for low speed flows. So, such flows can be treated as constant density or incompressible flows, that means as though the fluid medium is not showing any effect of compressibility. So, we will assume that, and further we will assume that the temperature is constant. So, constant temperature flow or isothermal flow, which has an impact on the viscosity coefficient, because viscosity coefficient is actually a function of temperature. So, we will assume it to be constant. Therefore, density we will assume to be equal to the free stream density everywhere. That means, far upstream of the body, whatever the value is, that is the value which is retained everywhere in the flow, and similarly the viscosity coefficient is also held equal to its free stream value. So, keeping that in mind, let us try to proceed, and we will see that if you write down the equation, the momentum equation, it will look like this. And then we are going to introduce a few non-dimensional quantities. We are going to non-dimensionalize the velocities with respect to the free stream velocity, the pressure with respect to free stream pressure and the length scales with respect to the characteristic length scale of the problem. For example, if C is the chord of an airfoil, we non-dimensionalize the coordinates x and y with respect to C. If you do that and you substitute these values into the original equation, then what do you get? You get so every term has to be rewritten carefully in terms of the non-dimensional values, term by term you have to carefully do it. And you should all be doing it at home, so that you gain confidence and you gain the practice for doing it independently. Now, if you take the common terms out, then you can write it as so, let us reorganize the terms on the right hand side. What do you have over here? This is a very, very important term in fluid dynamics. This is what we call as the Reynolds number, and because it is dependent on the free stream values, we call it as R e with a subscript infinity. This is the coefficient for the viscous terms, mind it, and you can show that the Reynolds number happens to be a ratio of inertial force and viscous force in the flow field. So, as the flow velocity increases, for the same fluid, the inertial forces will dominate over viscous forces. So, when Reynolds number becomes larger, inertia dominates over viscous effects, and that is where viscous effects become weaker and weaker, and therefore, you can say that for infinitely large Reynolds number, typically the viscous terms become 0. But for practical applications, even for fairly large finite values of Reynolds numbers, the viscous effects reduce to a very insignificant level for the overall flow field, and they get confined to a very thin layer around the body. So, most of the flow field behaves in an inviscid manner. So, this is the purview of inviscid flow analysis in aerodynamics. That is where it gains so much importance, because most of the aerodynamic flows are high Reynolds number flows, and therefore, inviscid flow has a dominant role to explain such flows. So, if you consider inviscid flows, we again look at x component of momentum equation now. But we look at a 3D inviscid flow field, and some of the assumptions that we have already made continue, that is, we are no longer looking at effect of body forces, for example. So, we will only look at pressure gradient effects, and now viscous effects are also gone, because we are assuming that the Reynolds number is large enough that their effects can be neglected. In such a case, the x component of the momentum equation can be written like this: only the effect of pressure gradient will decide on the acceleration of the flow. So, like you are writing it for x component, you can similarly write for other components, but here we need it only for this component to show the next analysis that we would like to do, that is to derive a very important equation for inviscid flows, which is called as Euler equation. Let us expand the left hand side. We know how to expand the substantial derivative. We know the operator, and that operator is now applied on u. So, based on that, the local derivative and the convective derivatives put together give you 4 terms on the left hand side. And further, let us assume that the flow is steady. Therefore, the del u del t term will go away from the equation. You are only left with the 3 convective derivatives on the left hand side for a steady flow. Therefore, if you just want to add on to the assumptions that you are making here, you are further assuming that the flow is steady. So, having said that, let us take the next step. What we will do is we will take the density to the right hand side, and therefore, you can take it out from these terms and associate it with the pressure gradient term on the right hand side as a minus 1 by rho del p del x, and then you multiply the entire equation with dx. So, if you do that, what are you going to be left with? Let us try to write it down. So, you are multiplying each of these terms by dx. That is what you will have after you multiply. When you are done with that, you try to keep 2 terms identified. You have a v dx here and you have a w dx here. So, keep these 2 terms in mind, and we are going to follow the flow along a streamline in 3D space. So, we earlier developed the equation of a streamline. So, from that equation, these should be ordinary derivatives, differentials rather. So, in 3D space, the streamline equations look like this, and we are going to make use of these 2 actually. This will not be required. So, if you associate these 2 equations with the above 2 terms which are indicated, you can rewrite this equation. So, let us try rewriting it. It will be u del x into dx plus u del y into dy and then u del z into dz. That is what you will have on the left hand side. U can be taken out as a common factor. Let us see what is the next step. Since we have assumed it to be a 3-dimensional steady flow field, u can be functionally represented like this in a Cartesian space, and if you take a differential of u, then you can write it down as del u del x times dx del u del y times dy. This is how you can write down the differential. Now, if you combine the last two equations, you will find that you can now write it as u du is equal to minus 1 by rho del p del x dx. Now, if you take this into the differential, it is du square with a half outside, right hand side remains as it is. Now, like you do it for the x direction, you can write this equation similarly for the other two directions. So, now you have it for all the directions. So, this should be del p del z into d z. You have to club them together. If you do that, if you sum them all, then what do you have? You have d of u square plus v square plus w square with the right hand side with the common factor minus 1 by rho. What will you have? You will have del p del x times dx, and you can get to see some clear indications that this equation is going to simplify. For example, it is clearly visible here that this is going to give you a dp. Similarly, here u square plus v square plus w square, the sum of the components of velocity will give you the velocity square, the total velocity square. So, what you have finally? You have half d capital V square is equal to minus 1 by rho dp. If you rearrange, you get dp is equal to minus rho v dv. This is a famous equation in aerodynamics, which is called as Euler equation. It has enormous utility in analyzing inviscid flows in aerodynamics, and then if you further apply it for constant density flows like incompressible flows that we discussed a few minutes back, you can take the density as a constant and then integrate the equation between states 1 and 2, and then it gives you another very important equation which is applicable for constant density situations. You rearrange and you get so it is telling you that p plus half rho v square is a constant in the flow field. This is the Bernoulli's equation for a constant density medium, and we can show that this p plus half rho v square is a constant along a streamline of the flow. Now, for rotational flows, it is a constant as long as you follow a streamline. However, for irrotational flows, the constant holds good for the entire field, for the entire flow field, which means for rotational flows, the points 1 and 2 lie on a streamline in order that this equation is applicable between the 2 points. However, for irrotational flow, the points 1 and 2 can be located anywhere in the flow field. Not necessarily on the same streamline. So, these are very, very important concepts. We will expand more on these concepts in a later lecture. So, with this we conclude this lecture saying that we discussed about the relevance of Reynolds number in this lecture and in approximating Navier-Stokes equations at high Reynolds number. And prior to that, we had completed our discussion on substantial derivative, and we showed that how substantial derivative can be used to explain a fluid element acceleration. We will take these concepts forward further in the upcoming lecture. Thank you.